Noida, Miss Manjima Chatterjee, Vice Principal, Shiv Nadar School, Noida, and Mr. Matthew, Head of Connected Learning, Shiv Nadar School. First of all, I would like to invite Miss Shashi Banerjee, Director of Education, to share with us her perspective on today's event. Shashi ma'am is known for her joyous demeanor and is much loved and respected by students and teachers alike. Shashi ma'am, over to you.
Thank you, Akanksh. That was such a lovely kind of introduction, but I wish to share with you that the rain is lashing against my window panes. I don't know if you can hear or not. And what a lovely morning when we are talking about all the magic in the universe, which we are getting to unravel, and from a literary pursuit of looking and pursuing the stars, the whizzing stars across the skies, which is what a Mark Twain would do, to coming right in here to look for that tiniest, minutest truth. Probably the truth keeps unfolding, and for which I would first like to thank Vinita Sharath. She's like that catalyst who starts off getting all of us together. And through Vinita, I'd like to really express our gratitude on behalf of all of us, the Shiv Nadar University, the Shiv Nadar School, the Vidya Gyan fraternity, and the students, everyone who's also joining us, Mrs. Gaukar and the others. Dr. Archana Sharma, you don't know, I know I shouldn't say much, but just to say, for most of the students that I have conversations with, science was never so fascinating. The story of the universe was never so fascinating as how it has become for them now. And I think when I look at what this celebration, that this decennial celebration of the God particle, there must be something about a deeper mystic truth about the Shiv Nadar School also celebrating its decennial year really since inception. And I think it was around that time that we got connected with the mysteries of the universe to say our students at best should make an impact and leave the world a better place by getting to know these deeper mysteries and doing something about it. Because how does this finding really impact the world is what you've been talking about. So I salute all the scientists. I salute the scientists who are partnering this entire Anushtan, as I call it, which is also, Vinita, you've got Dr. Nitendra, who always comes in, and you've got Dr. Patrick Das, who's of course such a great person to be here. And then you have these students, whether it's an Adi or a Naman, Vedan, and now from the SNU, Pantho, Akanksh from SNS, and Ekta Saxena from the Vidya Gyan, who are representing the many learners who are all over this place. So on behalf of all the learners, we are all learners, I extend a hearty welcome, and I look forward to deepening the learning, the understanding for even a lay person. Because as Vinita said, Dr. Sharma, the way you have the conversation with the researchers, the young minds, keep unraveling and simplifying mysteries, which sometimes unnecessarily get complicated in our minds. And we miss the real star for the nebulous, jargon around it. So I salute all of you. Over to you, Akanksh. Thank you for giving me this little space to express my gratitude. And you have started off a journey, and I believe it's going to go on for the whole year. So I wish you all the best in this journey as well. Thank you, Akanksh. Over to you.
Thank you so much, Shashi ma'am, for your kind words. And now what I would like to do is introduce Mrs. Gaukar. She's our guest of honor today, and she is a dedicated and popular teacher to a disciplined and effective administrator involved in all aspects of the school administration. Ma'am has had nearly a decade of experience in being part of the senior administration team, and I now invite ma'am to say a few words.
Thank you so much, Akshansh. And honestly, it's such an honor for me to be a part of this very illustrious panel of speakers, students, and school administrators. I was very taken by surprise when I got a personal note inviting me. And like Shashi ma'am just mentioned, I am absolutely not from the field of science, and science probably goes a foot above my head. But Vinita's passion when we were working together, and meeting Archana for the first time when she visited our school, and as somebody mentioned, Vedan was the moderator. I mean, those are incidents which actually sparked that little interest in me to understand a little. And Archana ma'am, I would like to say that after that particular visit is the first time when I even got interested in this entire topic, and I bothered to open my Google and start researching. So thank you so much for having me here. I'm honored and I'm flattered, and I'm really looking forward to hearing Archana and, of course, Vedan, who's been a very, very special student and very dear to all our hearts. So over to you, and thank you once again for having me. Thanks a lot.
Thank you, ma'am, for your encouraging words. Before we start out with our interaction with Dr. Sharma and Mr. Dewan, I request the audience to please feel free to put your queries in the chat box along with your name, and we'll make sure to address those. Over to you, Panthu, now.
Okay, so let us now proceed with the questions. Continuing from the last session, we are hoping to dive a little deeper into the story of Cern and understanding the Higgs boson better. So to start off, one thing that always fascinated me is how has Cern been able to create such energetic particles moving nearly at the speed of light? Can you please give us a sneak peek into the mechanism or mechanism used to achieve those conditions?
Thank you for the question, Pantho. Just if you permit me, because I am really carried away a little bit by seeing you all once again, and particularly I see Ekta here, whom I have met, I think in 2018? 2019.
No, it was 20.
So I have been to Vidyagyan, and it is so beautiful to see one of the students coming here and moderating the session. So I'm really touched, Ekta. Thank you so much for being here, and also the spark that you have towards the subject. So coming to the question is about how do we create these particles to move to the speed of light, right? That's the question.
Yes,
now, first of all, why do we have to do that? You know what we are trying to do? We are trying to recreate in the laboratory the Big Bang, which is, of course, not possible. First of all, if you imagine that, oh, good Lord, how can we make the Big Bang again? So we have to do it in minuscule way, which means that we take, you know, the world, the universe, the galaxies, and everything is made up of fundamental particles. Now, we want to recreate that soup that existed before the particles were not even there, so that the particles can form, right? So just as if we were smashing two marbles together to look inside what is inside the marbles. But if we give them so much energy that they just melt, and you would not see the glass, pieces of glass or the pieces of color that's inside. Similarly, what we do is that we take two protons, many protons, actually thousands of protons, and we make them circulate. And just like we were to collide marbles, we collide these protons. So imagine what games the scientists play, you know. The Large Hadron Collider is the world's most powerful particle accelerator. So there are many of these accelerators, as they are called, because they accelerate particles and then they collide particles. The Large Hadron Collider collides protons because when you circulate them in a tunnel, which has beams, beam pipes, highest vacuum on the planet, and these protons, they gather energy along the way, right? Along the way, which means you have higher and higher magnetic fields, which then pull these protons further and they are accelerated. That's why it's called an accelerator. So inside the accelerator, these two particle beams, which are in a very, very high vacuum, so that the protons are not lost in collisions, they come very close to the speed of light. And then they are made to collide. Now, how can that happen? Because they travel in opposite directions. So there's one bunch of protons traveling in one direction, and the other bunch is going in the counterclockwise direction. And then they are made to collide in certain pre-designed points. And how can that happen? When we have stabilized magnets, like quadrupole magnets, which focus the beam in such a way that the collisions can actually happen. Now, imagine at home you've played with magnets, right? Or, I mean, at least the kids of today know about magnets. We didn't grow up with that, but yes. So if we want to heat water at home on a heater, we are using currents of the order of 4 to 5 amperes. But to accelerate protons, we are using currents of the order of 22,000 amperes. So the current that we need to have the magnetic field that we would require to accelerate the protons. So we need superconducting magnets. And that's again another field, because we have to chill these magnets. We have to cool them down to minus 271.3 degrees centigrade.
That's just a few decibels away from the absolute zero.
Exactly. So we have to, connect everything to liquid helium, and we have the largest liquid helium supply here, because our accelerators have to work for 6-8 months to be able to give us enough data so that we can look inside and find the Higgs boson. So just some numbers. There are 1,232 dipole magnets. You've seen maybe in pictures this accelerator that's blue in color and very long. So that's 15 meters, and they bend the beams. And we've got quadrupole magnets, which are smaller ones, and they focus the beams prior to the collisions, right? And of course, when these beams are moving, they are made to collide in different locations. And those are the particle detectors, or the experiments, where I, as an experimentalist, work in one of them.
Okay, thank you, ma'am. That was a lot of new pictures. Just one question. The quadrupole magnets, they have a lesser field, basically. Their distance, it decays much faster than a dipole magnet, right?
Yes. Yes, sorry.
Yeah. So my question is, how is the quadrupole magnet actually used in the accelerator?
Yes. So you have quadrupole magnets which focus the beam, just like light beams are focused by a lens. Similarly, it's a lensing effect that is used to focus the protons in such a way that there is a probability of collision. Because you can imagine that even with all this, what I have described, there are very few collisions per bunch crossing. There's a very few collisions. So this focusing is very important. And the quadrupole magnets, they are not as long as these 15-18 meter magnets. They are smaller, but just prior to the collision, they squeeze the particles, and they increase the chance of collisions. You can imagine tuning the magnetic field, right? Just like a lens you can tune how far you want your the spot of light to be focused. You've done that, I'm sure, with a lens and the sunlight, right?
Yes, ma'am.
Exactly.
Also done a bit of quadrupole magnets, and the math is very difficult.
Yeah, you got to start at step 1 and then go ahead.
Okay. Thank you, ma'am. And one more thing, how strong is the electromagnet that is used in Cern in this process?
The strengths of the magnets, you mean?
Yeah, like if the total strength of the if we sum all the strength of the individual magnets, how strong is the magnet that is used?
So the strength of the magnets is in Teslas, obviously, and this is we need to get to 6.5 tera electron volt per beam. So that's the energy we would need to actually create the Higgs boson. So these particles have to go nearly 12,000 times per second. So we need to have series of interconnected linear and circular accelerators. And that's, of course, again, it's a lattice of magnets, So it's not just one magnet, it's a lattice of magnet which keep the beams precisely aligned. And each one of them is between 30 and 120 tons. So just imagine that these little objects, we've got a hangar like you use for airplanes, where we actually commission these and they were installed. So the magnetic fields are typically of the order of from few Tesla to tens of Teslas. So it's a very strong magnetic field that is then created. And of course, you can sum them up. If you want to just make an addition sum, then it will be that multiplied by 1232.
Oh,
Could I ask you a question, if that's okay?
Yes, then go ahead. That's the
Hanji,
purpose.
I had a question about, so you talked about the bending magnets, of course, and they stop the particles from sort of flying out, right? They're keeping them in that circular radius. You talked about the quadruple magnets, which focus down the particle beams. But the actual acceleration, is that not done by a sort of like electric field or a potential difference that's in the accelerator? Because from what I understand, the magnets won't accelerate the particles, right? So will it be a potential difference, or is it just like a plain potential difference, or do you use something slightly different compared to that when you're accelerating particles?
Then you're absolutely right. It is, in fact, imagine you have a battery powered magnet and you have a particle that you want to accelerate. And every time you flip the field and you keep moving it, it's exactly the same principle. Principles are very simple, applied to a complex application, which is the accelerator. So now when you throw in the equations, it does become a bit complex and you need accelerator engineer to create this, but beams are really accelerated with the simplest principle, which is to flip the field and make them accelerate.
That's fair. Thank you.
Thank you, ma'am, for that very elaborate answers. Okay, over to you, Akshansh.
So one thing that really stood out to me today was that Mr. Dewan is like, you have had an enviable experience in taking part in numerous competitions based on science and physics, like Anveshika, NIAST, Physics Conclave, and so on. So would you like to share your experience with students in these competitions and in such areas? And why is it important for people to participate in these academic-based events, especially for a school student?
Yeah, of course, sure. Thank you for the question. So, I mean, I think the first thing to understand is that me as a kid, when I was told to do something and I had to do something, I didn't really enjoy it. So when you're told to do physics in school, it's good and it's great. It's kind of interesting, but it's not as interesting as it can be. So when you go out and do stuff like NIAS, which was it was an experimental competition set up by IIT, where they just threw experimental scenarios at you and asked you what would happen. That was the first round. And the second round was sort of, they gave you experiments to do. But for the first time in my school journey, I didn't know what the answers to the experiments were. Because usually when you do experiments in school, you're trying to find what the value of small g is. We all know what the value of small g is. So it's very easy to be like, I was wrong because my answer is wrong. But when you're doing science on the larger scale, or when I'm working in a laser plasma lab, or Mam's working at Higgs, at Cern, it's not something that you don't already know all the answers. So it's very interesting to go out and actually see that to make sure you follow the method correctly, to make sure that you're being true to the science and coming up with an answer that is unknown or wasn't known to you before. And that's a very important part of science. So that's something that I did learn from doing stuff outside of school. And then when it comes to something like the physics conclave, I mean, that was brilliant because we got to interact with people like Dr. Archana Sharma, or even I think Dr. Patrick Das was also there that day. And it was amazing because then you understand why you're doing what you're doing in school, right? The first question everyone always asks you is like, why do I need to know calculus? No one knows why you need to know calculus. Most people won't use it in their real lives. But I sort of understood that if I wanted to go down the field of science, everything I'm learning right now is a very, very good base to me understanding stuff later. And you realize that when you go to even my first year of my PhD, I still was taking a calculus class. it happens till the end of your PhD. You will be using classical mechanics or electromagnetism, Maxwell's equations. These will all keep coming up through your entire career. I mean, even the most brilliant plasma physicists in the world will still be using basic Maxwell's equations when they're trying to solve anything. So it's always interesting to understand where you're going to go from here. And something like the physics conclave really helped with that. So I would say just go out and do whatever you find interesting and want to do, because as soon as you do that, you will have so many more options than you thought you had. Yeah, that's about it.
Thank you, sir, for that answer. I like, as a person who participates in a lot of these and is like dedicated to explore science in like action, I think this is like really inspiring, and I'm sure like a lot of viewers who are watching this will find it really encouraging and would want to participate in more of these. Dr. Archana, if you have any thoughts to add here, I think you were part of physics conclave too. If you have any thoughts, please feel free to add.
I'm really delighted to hear Vedan's journey, and I think we should really not focus on what's coming in the future, but focus on the learning. And I feel that indeed, even when I studied all these Lagrangian equations and advanced, integral and differential calculus, it was kind of daunting because I was not able to relate it to real life at that point of time. But then when you continue in your journey, and there are moments in life when things just click. So have the confidence to imagine that scientists or researchers, teachers have all contrived in your favor. So we should just keep going. And I think I'm really, really happy to see that, to believe whatever we learn at various stages of our lives, keep an open mind, and also do fun activities, because when you enjoy doing what you're doing, you will learn in a natural way. So great journey, Vedan, and an example for all the other students too.
Thank you, Dr.
Thank you so much, ma'am, for your insight. Over to you, Ekta.
Thank you. Before we continue further and deeper in the journey, ma'am, I'm very keen to know, why is the LHC underground?
Okay, so first of all, the LHC is a second generation accelerator from a previous accelerator that was housed in the same tunnel. So the tunnel was already built in the 80s when the previous accelerator called LEP, Large Electron Positron Collider, that was housed in the tunnel. So the tunnel was already there. Now you would ask, why did they make it underground already before that? So as you know, that Switzerland was neutral during the Second World War, and it was decided to keep and create a center of excellence in Europe, okay? Because the European scientists were all running away to United States, and they wanted to retain the scientists in Europe. Retaining nuclear scientists, particularly in that time. You may have heard about the nuclear bomb and so on. So science for peace was established as a motto for Cern, which was established in 1954. It happened to have its seat in Switzerland. Switzerland is a very tiny country. You know, the population is only 8.5 million. The population of Delhi is, I think, nearly 17, 18 million, if I remember well. So and the country is very tiny also. It would, I don't know the square kilometers, but you can imagine if you just take a quarter of Uttar Pradesh, that is Switzerland. So now where do you go looking for space of 27 kilometers, first of all? On the surface, you have to break buildings and houses to build it, correct? And then you will have to build even more structures to make all the safety requirements for radiation. So if you were to build it underground, you just dump your beams in the earth, and you are able to have all the space that you need. The only overhead is that you have to, but once you make the tunnel, you can reuse it. So for the last 30 years, we are using the same tunnel, previously for another collider where a lot of standard model physics was tested. You know, there were many new particles discovered. The standard model has been, a fantastic keystone of particle physics. Just like the periodic table in chemistry, we have the groups and the periods in chemistry. In the same way, we have the standard model where we have all the particles in a very nice, neat way. And we have been testing that using this tunnel underground. Does it make sense? If you have more clarity, please ask me.
Yes,
Add
ma'am.
something to
Yes,
that,
ma'am.
if that's okay.
Thank you, ma'am.
Yeah, just in general, I think that it really worked out really well. Like ma'am said, that I think Switzerland had I remember reading about this. Switzerland had not everyone's ready to give up their property. So that was not something that they wanted to come and sort of contact with. But also it worked out hand in hand with the science, because when you have particles moving in these circular trajectories, they emit something called synchrotron radiation, which is not good for people in general. So when you're moving at that high speeds, you're going to emit radiation. And of course, you can set up decent walls that will be able to block off the radiation, but the best wall you can have is just being underground and letting the radiation sort of hit the earth itself. And of course, you can dump your beams into the earth. You don't have to worry about humans tampering with anything or a bird landing somewhere it shouldn't. So it all sort of worked out together to just be underground.
Yeah. There we have had our bird hits, by the way, because one of the transformers, was hit by a bird, and she sat there. A weasel was also fried in our power generator. So there are little stories for the amount of infrastructure we have on the surface. So imagine if the whole LHC was on the surface, we would just be troubleshooting all the time. But within the synchrotron radiation, yeah. And people in general are scared of radiation, the average public. So if everything is underground, even though it's not dangerous, even though we would mitigate whatever needed, but it's important to have the public go along with what scientists want to do, because in the end, it's the taxpayers' money that we are using, right? So we are able to then buy into the confidence of the people living in this area also. So it's, of course, the scientific background is there. In addition, it's the confidence of the government, of people as well.
Thank you.
If I might ask, yes, Ekta, I am not a science student. All of this seems magical and seems completely at times, something that I feel comprehending it would require certainly a greater development of my brain. But as a layperson, right, if I can call myself that, Dr. Sharma, what work are we doing in India in this connection? Are we doing good work? Where are we doing it? And, where are we in this understanding?
That's a brilliant question. And certainly I would like to answer it. It would take a complete lecture, but I would try to be very simple, because, Indian science is very, very good and outstanding as far as our theoretical contributions are concerned to science. Certainly, you have heard about Homi Bhabha, about Satyendranath.
Correct.
The Higgs boson, when we call it the boson, it's because of our Satyendranath Bose, because he explained how ensemble of particles behave. He created Bose-Einstein statistics, which is unbelievable contribution to the whole world of particle physics. So there are many, many examples. There's another lady called Rohini Godbole. She is a Padma Shri as well. And she has contributed greatly to the understanding of how the Higgs boson can be experimentally observed. She worked from the 70s, 80s, and so on. And finally, when the Higgs boson was observed, she has contributed to understanding how to do it. And there are several institutions in our country that are pioneers in doing the data analysis of the data that comes out from the LHC. Tata Institute of Fundamental Research, Delhi University, Punjab University, Chandigarh, Jaipur. We have in Kolkata also several institutions. So I won't name all of them, but let's say we have a good number of institutions who have an engagement at Cern. Financial engagement as well, where our funding agencies like the Department of Science and Technology and Department of Atomic Energy, they are funding as an associate member, they are funding CERN, and we have opportunities for everyone Let's talk about Shiv Nadar University students. You also have the opportunity to do project work, to do a semester, to do your anything. So indeed, there are about 130 Indians who are registered at CERN, and another 250 all over the world, who are working with CERN on Indian passports. So indeed, we can go much into detail on what they are doing, which experiments, accelerators, etc. But I'm very proud, and it can go in one direction. It's very good.
Thank you so much, Dr. Sharma. It makes me very proud also. It really does. And I just feel that, wow, we are definitely, a nation of great scientists. The more I read about it, the more I understand that. And Dr. Sharma, I'm now going to read a little bit about all that you've said.
That's wonderful. Good. That's wonderful, Payalji, and I would encourage you to take a look at the news stories from India and CERN. Find that we have done a good job. There's always room for improvement. I will add that.
Thank you.
Ma'am, if I may, I would also want to add on the thing that we were talking about. Currently, I'm in my fourth year, I'm doing a thesis. I'm doing my thesis on compact objects. So Chandrasekhar limit, again, named after the scientist Chandrasekhar. It's a very important concept, and it's such a simple but a marvelous concept which changed the whole theoretical and astrophysics field in general. So that's quite fascinating.
Of course, yeah. Yes, Vinita ji, I see that you're...
No, actually, I was just, I'm so happy and proud to see Payal ma'am and many of people who are basically from language and the humanity background. And just to let Payal ma'am introduce to audience, she is a hardcore language, you can say, a person who is working at core office, looking after communication and language. And she then heard Dr. Archana Sharma. She said, I'm so excited to learn more. And she started exploring physics book on particle accelerator and all. And she said, can I join on Zoom and not on YouTube? I said, why not? In continuation with this, Ms. Arpita is on YouTube. If there is any question from any student on chat box, Ms. Arpita, please paste it on the common group. So students' question can also be taken into account. In addition, moderator, please, whenever you are asking questions, take the view of both the moderator, because everybody has got different view. Do not. So this is my gentle reminder. Over to you, moderators. Thank you.
Vinita, can I have a 10-second to say that Dr. Sharma, Payal is also not just the language person and the theater person, but is also somebody who looks deeply into the professional development of our educators. So also leadership development. So I think that's where.
Thank you. And such a pleasure to meet you. In fact, this is one of the most important aspects to encourage, to make sure that whatever students learn, that can be, consolidated, and that can only happen from another lateral angle than what they understand in class. So it's very, very important, and so happy to meet you, Payalji.
One last announcement, if you all permit, on moderators. I'm sorry, Sasima, would you like to add something more? Please. Okay, thank you. So please make sure that the session is over by 12:30, because Dr. Archana and Vedan have to leave with, and they agreed for an hour, because it's 1:30 or 2 p.m. a.m. at night for Vedan, and for Dr. Archana has to leave for her office. It's early morning, and she has just agreed. Over to you, moderators. It's not important that how many questions you cover. It's not. Ma'am is ours, Archana ji is ours, so is Vedan, and so are many others too. But what is more important, that what questions you are asking, and if there is some queries from school students on YouTube, please see that those are addressed.
Of course.
This is a continuous webinar, and it's not going to end today. Over to you, moderators.
Thank you, ma'am. So it's with a simple Google search, one can find out that CERN has total 8 detectors, the main 8 detectors, and 2 of them, being Atlas and CMS, were involved in the discovery of the Higgs boson. So why are they special? Why were only these 2 detectors used? And what are the main differences between them?
Yeah, thank you for this question. And before I go into this question, I would like to maybe make a comment on what we discussed previously, just a small comment, that there is a question on why at all are we doing all this, right? So you would wonder why are these people going, thinking so much about the Higgs boson and how does it connect to me and so on. And I would like to maybe address to Payalji and to Anjuji, in fact, who is also in the audience, that when you go to the hospital, you have, you see so many applications there. For example, the MRI or the X-ray or security, or, even looking inside our body, all these techniques have come out because we use particles there. X-rays are also some kind of, viewing instruments. The COVID-19 came from the blue. Nobody had any idea what was happening around us, when COVID hit us. But then there was an electron microscope, right? And how electron microscope made, scanning electron microscope or the cryo-electron microscope? They were made because we made superconducting magnets. We knew how to cool things. We knew how to freeze the virus. We knew how we will be able to scan the structure of the protein of the virus so that the vaccines could be created. We do not realize immediately the connection between what we are doing here, not only at Cern, but all over the world in the realm of science, and the impact it has on society. So in the end of the day, whatever we're doing, today we are speaking to each other is also, in some sense, courtesy science, because WWW was invented at Cern since the physicists wanted to share data with each other. And how do we share data with Vedan sitting in the United States and, you all in India and, and so on? So they developed a protocol called HTTP, which now an average layman person also can recognize. Oh, that's a website. So it's the infiltration of whatever we do in terms of curiosity of mankind, in terms of understanding what we want to do. And then it has a great impact in our lives. And we will have a session only on that next time, moderators and Vinitaji. So back to your question about Atlas and CMS. So suppose if I discover a new species of an elephant somewhere, and the Indians say, oh, this looks like an Indian elephant. And the Africans say, oh, this looks like an African elephant. And it makes different, hypotheses that because its trunk is like that, and the tusks are like that, and the tail is like that, and so on. But they do agree that it is an elephant, right? So now, if our famous Higgs boson is discovered in one of the experiments, right? Then how do we know that it is a Higgs boson? Somebody else with different criteria and different experimental methods should find the same results or similar characteristics. So Atlas and CMS are two different multi-purpose experiments, which means that they have technologies which are very different to look for the Higgs boson. So CMS is a compact, it's called CMS because it's compact muon solenoid. It means very high magnetic field, and you contain the decays of the Higgs boson inside the experiment. It's a 14,500 ton experiment. Imagine one jumbo jet is 250 tons. So that's the kind of experiment. And of course, there are different detectors, which are like, our mobile cameras or microscopes with which we take pictures 40 million times of every collision. So when we pick up so much data, we need so many students like you all to look at the data so that we can look for the Higgs boson. It's like finding a needle in many, 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 many haystacks, So yes, it's fantastic. And CMS found it using different techniques, and Atlas found it using some other techniques. And we can go in more detail, but maybe I'll stop here to allow other questions. Yes.
Thank you, ma'am. So it's basically looking at the same thing from two different perspectives to narrow it down even more. Okay, thank you so much. Now I have a question for Mr. Dewan. I really want to know if the standard model complete with the Higgs boson. Is there a possibility of it to be proven untrue?
So I guess Higgs boson was a big puzzle, like a big part of the puzzle, right? So like once you finally got the Higgs boson, it was one of the biggest achievements we had in the past. And but a lot of people will argue whether or not the standard model is still complete. For example, there is fundamental forces like gravity that we know exist, but we don't have a particle in the force carrier particle library that pertains to gravity, right? So they call that the graviton when it comes to particle physics. So the thing is that gravity in itself is a bit weird to sort of detect when it comes to the standard model, because the standard model is all based off what we know as quantum mechanics, right? So that deals with really tiny things, and in itself and by its nature, it's discrete. That means that everything happens in steps, right? It's not continuous. That's what quantum mechanics is. And then the best theory that describes gravity that we know of is general relativity, right? So that was Einstein. But general relativity is completely different from quantum mechanics in the sense that it is all about the continuum of space and time, right? Everything's continuous. It's a fabric, and that describes gravity. So now how do you put these two theories together? It's very hard to do, and no one's been able to do it. Theoretically, they're trying. There are theories called quantum loop gravity that try to put them together, but they're very hard to put because this is discrete, this is continuous. Their nature is different in themselves, so you can't really put them together. So one of the reasons that a graviton might not have been detected in the standard model could very simply be because we still haven't unified quantum mechanics and general relativity, and they're very hard to put together. But another very simple reason could just be that the effects of the force of gravity, if we can call it a force, a lot of people argue it's not even a force because general relativity says it's not a force, right? So if you can call it a force, the effects of that force are so negligible compared to something like the electromagnetic force, the weak force, and the strong force, that it would be so hard to detect it while these other forces are at play. And they will always be at play when we're talking about particle physics. And so there are these two reasons. One's quantum mechanics and general relativity, and then one's the fact that gravity is so negligible at these small scales. So now answering your question, will we ever find a graviton? I mean, not me, it's not the work I do, but them at Cern, of course, but will they ever find one? It's a very hard question. It's a very open-ended one too, because why do we have gravity, right? It's another thing to think about. Gravity in itself is a consequence of mass, right? And mass we know is a consequence of the Higgs field, right? So maybe in some way Higgs is the gravity particle. We don't know that. It's very possible, right? It's very possible they're all connected. And the graviton in itself isn't some fundamental force. It's a force that's a consequence of another force carrier particle, that is the Higgs boson. So is the standard model complete is a very open-ended and very hard question, but it is possible that we find a graviton, or it's possible we don't. But I know that the CERN's going to have a third run now. So when they do, and when they understand more about the Higgs boson, it might answer how gravity comes about or why it comes about. So yeah, that's my answer. My answer is that I can't really answer you. It's a difficult one, but yeah, that's all I can say about it.
If I may, that Vedan has given the correct answer. It's not because he doesn't know, because we don't know. That's the whole point, because we do not know. And maybe just I can take 30 seconds to bring in the Higgs, why the Higgs, especially for non-science people in the audience. You know, the Higgs really is something that gives mass, like Vedan just said. Now you would think, what a concept is this? Higgs gives mass. How does this happen? So I just want to bring back my famous analogy where imagine that all of Shiv Nadar schools and all of Shiv Nadar University and all of other students that you know, they're all standing in one stadium, right? They are waiting for a big star to arrive. And the big star could be, I think across generations, Amitabh Bachchan ji, okay? So everybody knows that he's coming. So just the knowledge that he's coming makes them move in a certain direction and talk to each other. Oh, he's coming, and so on. While the younger kids, you know, in classes 1 and 2, they would not care so much, right? Because they might him and so on. So the moment he comes closer, there's more, you know how things are reported. Somebody at the gate will say, oh, he's coming in another half an hour, he'll be here, or 10 minutes, he'll be here. So the more the chattering increases inside the stadium. And it will be different on different corners, right? It will be different because some people are like crazy fans. They will be shouting and doing things while the others might not be doing the same expressions. So when he actually enters the stadium, there'll be a big, like literally stampede over there, probably. But you can imagine what I'm trying to explain, where some people will rush to him, give me an autograph, I want to shake my hands. Some people will be on his feet or something. And while others who don't, like the kids and all, they might be still playing and doing other things. So imagine now, this is the field of a star. And let's imagine that's the Higgs boson. And the Higgs boson and this whole stadium is a soup of particles which existed at the time of the Big Bang. So the star, like the Higgs boson, exerts a field on the particles. And depending on how much they like, the fan quotient, if they like him too much, they'll be attracted and they'll get more weight. They'll get more mass, not weight. And so the protons, for example, or the quarks, as they're called, have more weight. Some other particles might have even more weight. The top quark is very heavy. And then there are particles like the photons or neutrinos, massless or nearly massless, like the little kids who couldn't care less, So that's just the way we describe all this in mathematical terms, and then the Higgs mechanism gives mass to particles. So Higgs can be one and there can be many Higgses. So that's what we need to somehow study in this run 3 that has just started on July 5 at Cern, and we are all taking data, and everyone is invited to look at the dashboard of what's happening at Cern. Sorry for the interruption.
Thank you, ma'am. That was really eye-opening. I don't know whether this question is right or not, but I would really want to know what is the fan quotient in physics terms, in mathematical terms. What all can contribute to it?
Loads of things will contribute, to it. And this is probably the subject of another lecture, because this really goes into, you have to learn about the quantum mechanics and so on. So, the mass of the particle, the distance from, of collision, the probability of interaction, it gets complicated at that point. So maybe another time I'll come back with equation. Actually, there's just one big equation which can describe this, but I do need to have it around here. So next time I will show it to you. Yeah.
Sure. Okay, so.
May I, Panthu, there is one question to Vedan from one of my 7th grade students. He's asking that little bit I'm understanding, little bit I'm understanding now what they are saying. Can we have it in much more simpler way with Vedan and student and obviously Dr. Archana? And he's again writing that I'm excited to learn more physics and I want to study physics in future. And I'm so happy that though I understood a little bit, but I have joined the session. Thank you. Over to you, Vedan.
So, I mean, what part would you like me to explain simply? I guess I could start with, as Archana ma'am said, she very well, the way she describes the Higgs field is very interesting. I think what we need to understand is that any particles sort of are in themselves like they're either particles and fields sort of go hand in hand, right? They're sort of very similar things. Particles lead to fields, fields lead to particles. We need to understand that. And what I talked about earlier, what I was talking about the standard model, right? That was just simply to understand that we as human beings find it very hard to understand what something means when it's continuous. We don't understand that as human beings, right? We'll always be like, oh, something is continuous, it must be made of something smaller. And that in turn must be made of something smaller, right? It's human nature to not perceive or understand what continuous is. It has to be smaller steps and discrete steps. And that's where something like quantum mechanics is, of course, a big word, but that's the field that the standard model uses to explain all of its phenomena. And then the continuous part is how gravity is explained. So I guess the thing is that putting these two things together is very difficult. Right? When you're saying that there are particles, but then you're saying that, wait, there are not particles, it's all continuous. It all just happens in one motion. So putting these two things together gets very hard. And I think that's one of the reasons that it's been difficult to sort of tell where the standard model will end and where we'll finally completed it. I don't think we'll ever complete it. I think it's always going to continue. I think it's very arrogant of us to think that we as humans can find every possible particle that is in 50 years of research. I think that's a bit arrogant to think that. And I don't think any of the scientists are working on it think that. They think that it's something that is going to take millennia of research. If we're here for a millennia, we'll still have something like Cern that's trying to figure out something new. So yeah, that's about it from me. But of course, Dr. Archana, if you want to add something, that'd be lovely.
No, you said it very well. Thank you.
Moderator, please note the resource people have to leave by 12. So may I request you to take, there are some questions which I'll obviously copy it and share with them. But at the same time, please keep track of time. And if possible, if we can wind up, and the session will be again in the month of September with our own dearest Dr. Archana Sharma and maybe one student or maybe some scientist. So please take note of time. Over to you, moderator.
Thank you, ma'am. Over to you, Akshan.
Right. So I'm just gonna quickly go through like one or two questions right now. So one thing I love about Cern is that I'm like really excited about is it creates and uses so much science fiction wordy materials, like superconducting magnets where resistance is almost zero, and like superfluids like helium-4. Like what other new impossible physics Cern is developing right now that might come in handy in our daily lives at some point? That is something I'm really curious about.
Thank you, Akshansh. This is a subject also dear to my heart because, whatever we do, it is in the end to this, betterment of society. And we need to leave the planet better than we found it, right? It was already mentioned by Shashi ma'am earlier. And Cern is no exception because though we are advancing the frontiers of technology in every possible direction over decades, when the LHC was designed, we did not know how we are going to design the magnets. No material existed that could sustain that mentioned earlier. So material scientists got to work along with industries to create a cable that could withstand those kind of currents and temperatures, because they would get hot when you have that kind of current going through the wires, the cables. The wire of the LHC is a winding that is so long, so thick, it's I don't remember 3,000 kilometers of winding of this kind of wire, right? So now that is used in many medical applications. So as I said, we take for granted when we walk inside an airport or a hospital, but all those technologies are coming from experiments or particle physics at Cern. And one point I want young people to note is that the GDP of the country is related directly to the science output. In Europe, it is 17 trillion. In India, we are very low there, and you are the hope, the younger people are the hope who are going to engage here and who are going to look at not only making money for yourself, but, contributing to society. That happens, our own growth happens naturally when we have the right, foundation and the right direction that is set. So for the industries, I can't tell you more because medical industries I already mentioned. Then you have arts, old paintings. Let's think of very old heritage paintings or buildings. How do you know how old they are? You are able to do using techniques developed in accelerator science to look at the layers on how they have been created or whether they are a fake or not. So that's one kind of application. Detectors that we use to look at collisions can be used for monitoring doses for astronauts. And in fact, it is being used. One of our detectors is being used in the International Space Station. And what else? COVID-19, of course, there was loads and loads of packages which were used for establishing the risk of COVID inside volumes, like a room or a hospital or schools, and these are being given free to the world to use. There are many, many other applications too. Now, in the future, artificial intelligence is coming up. Meteorology, for example, data management is a forte of Cern because we create the largest volume of data on the planet. You know, in 1 year, we are creating more than 300 petabytes of data, and we are moving to exabytes now. So what does that tell us? It tells us that we know how to manage data, how to share data, how to sift data, how to curate data, etc., etc. It is being used in weather forecasting, cyclones, and so on. And of course, money and lives can be saved, of course, once we have, these kind of advanced information. Sorry for taking more time. Yeah. So of course, this is not the end. There's a long list, and we can have another discussion on that.
I could add something small to what ma'am said, just very quickly. She did, I mean, she summed up everything that's basically happening, but just like way in the future, if you think about it, something like the Higgs, right? It's what gives things mass is what we understand right now. If we can understand why it gives things mass, then we might be able to make things have lesser mass than they actually have. If that happens, one of the main sort of restrictions of us exploring the universe is that we can't travel fast enough in our lifetimes to get to far places. Things are very far off. But if we understand how the Higgs works and how the Higgs field works and why something like a photon doesn't interact with it, if we can understand all this, then we might be able to create something that itself doesn't interact with the Higgs field and maybe then travel at speeds of light or close to the speed of light. So of course, that's something very far in the future, but everything we've ever done has always been very far in the future. A supercomputer 60 years ago was just not feasible, right? It was not something that people ever thought would exist. If someone was working on semiconductors, they'd be like, why is this person spending his entire life working on semiconductors? But that's the reason we have supercomputers and phones. So even something like the Higgs could be paramount in us understanding the universe and maybe finding another planet to live on. Yeah, anyways, that's all from me. Thank you.
It's absolutely amazing. I think I got chills thinking about that. And I think I'll conclude the session right now because I think we're going over time. So like this is one of the most engrossing sessions I've ever been a part of, and it was such an honor to hear everyone's wonderful insights, and like so many new concepts were explored here, and it was like absolutely mind-blowing for me. And right now, what I would like to do is I would like to invite Mr. Matthew, the head of Connected Learning at Shiv School, to share his reflections about this event today.
Well, can I start with a wow? It's great to see people engaged, students of all ages. You know, I consider myself a student. I think Paul's there. I think Dr. Sharma, great student. She's got 2 PhDs and still learning. I think what's great about this, it's inspiring us to learn through inquiry and discovery. Not knowing the answer, I think, is a great start. It's not a textbook answer, as was well explained by our students, and the relevance. I think that's been said right throughout, the relevance of what this work is doing. I'm also hopeful that we've got some teachers watching this on YouTube that are inspired as well, because it's about constructing the learning environments like you have done on this webinar that makes people think deeply, that makes learning fun. And of course, the result of that learning is for everyone. As I said, we've got a range of learners here. We've got a Princeton student who's a bright physics scholar who was Miss Vernita's original student. We've got our PhD lady here, and I can't wait to see her in front of me in person. So I look forward to the weeks ahead. We've got all our moderators, coming from SNU, coming from Vidigan, coming from Gurgaon, one of our schools. The range of learners on a classroom of this nature is fantastic. It's certainly far removed from a school system where we've got the same people of the same age doing the same thing at the same pace. So for me, you guys are very good exemplars of what the learning environment should be and what our schools should be. And I certainly love the connection to India. I thought that was lovely to hear and hear people say that they're proud. to be Indian and what the contribution is. And I think everyone, again, should realize India is a big player in science and in the world. So that is something for all of us to continue to understand and learn. So let's keep learning, because today's answer might not be tomorrow's. And I think, again, I'll just finish off by being proud and that word, wow. So congratulations to all of you. Thank you.
Thank you so much. Lovely to hear you, Mr. Matthew. And this is, I hope next time we can meet in person too. I have very fond memories of my visit to Shiv Nadar School. And this session was indeed brilliant because we have such eager learners like me as well. So I got to learn something from Vedan too. Thank you.
Thank you for having me. Thank you so much.
Just for one sec, would like to listen Anju ma'am, Anju Soni. Anju Soni is there?
I am very much here, Vinita, at your service. Honestly, like Matthew said, wow is the only word that can summarize today's session. And thank you, Dr. Sharma. Thank you, Vedan. Thank you to the moderators, Ekta and Panto and Akansh. I hope I pronounced your names correctly. And a special thanks and gratitude to Mrs. Madhur here, who's joined us today. Thank you so much for being here. And of course, Shashi ma'am and Matthew and Payal ma'am. And I just want to add one small thing, Dr. Sharma, if I may. So Payal ma'am is not the only literature person who's getting interested in science. Here's another one who's never ever been able to wrap her head around science. But I think thanks to your webinars and the way all of you put it, so simply demystifying the most difficult concepts of science. Thank you so much. And I hope that someday we will have a session about whether there is a parallel universe or not, because that's something that not only intrigues me, but maybe scares me a little. What if there's another Anju Soni somewhere and I bump into her someday? What's going to happen then? So thank you so much.
Yeah, such a pleasure. Such a pleasure. If the other Anju Soni is made of and if you shake hands with her, that would be interesting. That would be the next movie that will come out, So great.
Thank you for that. Thank you, Vinita. And back to you.
Without wasting time, would love to hear 2 lines from Payal ma'am, our own Payal ma'am, whose passion for physics has created more love from my side to Payal ma'am. So Payal ma'am, just 2 lines before everybody goes to office. They go to sleep because it's 2:30 p.m. AM in Princeton, and Archana ji to Cern office. Over to you, Payal.
Thank you, Vinita. Thank you. I would add to Matthew and Anju's wow by saying super wow. Actually, it's been such a privilege for all of us, for our students. We are so lucky to be able to interact with you and to understand the practicality of all that is being done. And I got hooked on this actually to an extent when we had a session at Noida, right? A while ago. And since then, I started my reading. And then Vinita got me even more interested in this. Had I had you as a teacher, I think my love for science would have certainly developed. I hated science, right? Because I couldn't wrap my head around it. It was too abstract for me at times. I'm very happy that one of our young students has already been inspired and has spoken of wanting to take up physics. What you do is truly magic, but today I'm beginning to understand the impact, right? I loved your analogy, by the way, about the stadium and the fans and the superstar. So that made it easy for me, and I'm sure it's made it easy for lots of our non-science students to also understand. I think that's brilliant. I'm hoping that at times there will be a time when we can actually have more conversations about things that intrigue people like Anju and me. Parallel universe, where does the universe begin? Where does it end? How did the universe start from one single point? Is that really true? I don't know. I'm sure it is because scientists say that, but I can't really figure that one out. And is teleportation, is that what's called? Is that possible? Will that happen? All of that, right? So that would be really exciting. Thank you so much, Dr. Sharma. I'm looking forward to our next interaction. And Vedan, great. It was wonderful listening to you. And Pantho and the other moderators, Akshansh, thank you so much for making it such a seamless experience. And before I say thank you once again and goodbye, I would like to say hello to Madhur. Madhur and I worked together for several years in my previous school. So hello, Madhur, and thank you, Dr. Sharma. Thank you, everybody. I'm so glad I have been part of this. Thank you.
Thank you, ma'am.
On behalf of Shiv Nadar Foundation and School, we are going to invite now Mr. Vedan or Vedan, my student, whenever he comes to India. We are going to spend a few hours with us in physical presence in campus.
Yes,
And
of course, I'd love
obviously
to.
when Dr. Archana comes, and that time, if one of you are there, that will be privileged. So this is on behalf of Shashi ma'am and Anju Soni, and we are inviting you.
No, of course, ma'am. Thank you so much.
One last thing, Vinita. You know, you're going to have to send me, and Shashi and you, I'll have to hypnotize, but you're going to have to send me to Cern. Right? That's going to make, I think, things really exciting for me. So Shashi ma'am, if you're there.
Ma'am, you and I will hypnotize Shashi ma'am and Vinita together. Don't worry.
Done.
We'll join our forces.
Okay, done.
It's coming very soon. So Payalji, it's coming very soon.
Oh, great.
I'll be very happy to welcome you, all of you, in fact, to come to Cern. Yeah.
Thank you, moderators. Brilliant job. Thank you, everyone. Thanks a lot, Madhur ma'am, for joining us at a very short notice. And thanks a lot, dear Vedan. It must be late night, so please go to sleep. Good night.
Yes, of course. Thank you.
And Shabba Khair, and we'll meet here in Noida or in somewhere in Delhi when you are coming here.
So I want to just say a big thank you to all the Vidyagyan participants, because they, you know, as I said, I went to meet them, and I met Ekta when she was there, and I do have some nice pictures. I'll pull them out and I'll share them with you as well. So wonderful, wonderful meeting everyone, and great motivation for me too, because, you know, I'm also looking to make a difference, you know, and that you are giving me an opportunity to do that. So thank you so much.
Also, I sometimes forget to thank Archana ji. The reason is she's also guest lecturer and she's also host, because this is in Life Foundation and SNS together are planning and doing these sessions after many meetings with me and Archana ji. So Archana ji is as well as a resource person, and she's also a host for the session. Thank you, Archana.
Thank you.